Hey guys, welcome back to our acids and base units here. We're going to kick off the day talking about the pH scale. So, up to this point, we've only looked at the concentrations of hydronium ions and hydroxide ions in water. That's been our big thing, right? We were looking at the ion product constant of water and how you could use that to tell how much stuff is associated and things like that. So this means we're getting really small numbers for the concentration of hydronium, or H plus, or H3O plus, and hydroxide. Now, once you get into talking about actual acids and bases, those numbers are going to fluctuate quite a bit. So, is there an easier way to represent those concentrations instead of always writing 1.0 times 10 to the negative 7 moles per liter? Is there an easier way to represent that? And so this was a problem bugging a guy named Soren Sorensen, one of my favorite names in science, in 1909. He was working for Carlsberg Laboratories after Carlsberg beer, because brewing is one of the oldest chemical industries. And he was obviously doing pH tests and stuff and trying to figure out the acidity of, I'm guessing, beer that he was working on, and decided that it would really make sense if he had a scale that had both the amount of acidity and amount of basicity contained in a single value. So we could easily look at one number and see how acidic or basic is this particular liquid that I'm working with. And so he, played around with numbers a little bit and invented the pH scale. And that's it right there. pH is the negative log base 10 of the hydronium ion. That's it. That's the entire thing. So you take your concentration of the hydronium ion, whatever that concentration is, you hit the logarithm button on your calculator and flip the sign, and you're done. So yeah, everyone's calculator should have a button that looks like this, or sometimes it looks like this. That's the one you're looking for, log base 10. There are other logarithm buttons sometimes, there are ways to do logarithms with different bases. Don't use those. If your calculator has a log base X or something, don't bother with it. It's log base 10, or if it just says log, it's assumed you're in what's called base 10. That's what we want. We'll never change that. That's it for pH. So little side note on logarithms that we're going to need in a minute, because you're going to have to go both ways, right? From hydronium to pH and from pH back. So how do you get rid of a logarithm? So you know how adding is the opposite of subtracting? Well, logarithm is kind of like the opposite of an exponent, but with a bit of a twist. So if I say the log base 10 of 100 equals 2, that's a true statement. Basically what this correlates into is that 10 to the power of 2 equals this. So because we're always in log base 10, 10 is always going to be the base of our exponent. Whatever the answer is, in our case, the pH, is up here. So 10 to the power of pH should give us our, whatever's in the middle, which is our concentration of hydronium ions. Now, the only thing you got to be careful of is there's a negative sign there. So when we actually work backwards, what we end up doing is we move the negative over here first. So you're actually doing 10 to the power of negative pH. So that's a real handy formula. If you want to write that one down, jot it down somewhere, that'd be one to keep handy. Both this one and this one will basically be all you need to know to get through pHs in this unit. So 10 to the negative pH gives you hydronium, or the negative log base 10 of hydronium gives you pH. So, for those of you who haven't worked with logarithms much before, this is probably all a bunch of gobbledygook, so let's give it a shot and see what it looks like. Example, what is the pH of a solution that has a hydronium ion concentration of 1 times 10 to the negative 5? All right, start with our formula. pH is the negative log base 10 of 1 times 10 to the negative 5. Cool, so you grab your calculator. You type in 1 times 10 to the power 5 negative equals. So I'll make sure I have the equals button so I have this whole thing in my calculator screen. And then in my calculator, I just hit the log button. Equals the negative of negative 5. This is one where you don't have to worry too much about the negative sign. It's a pH. You know it's going to be between 0 and 14, right? If your answer is negative, you forgot this. You just turn it positive and you're good to go. It is exceptionally rare to get a negative pH. There's some crazy acid cutting edge chemistry, university level stuff that can get you a negative pH. But we are not, no, it's not, don't worry about it. For now, you'll know that your pH is going to have to be between 0 and 14. So yeah, again, just to get it behind your calculator, you're going to have to get used to how to use your calculator, because you might have to hit the log button first and then type this thing in, or like mine, I type that in first and then hit the log button. It's one of those things where you're going to have to get used to your calculator, but give it a shot. You should be able to get to pH equals 5 for this particular question. All right, now we're going to look at the backwards. Solution has a pH of 3.5. How much hydronium ion is actually in that solution? So, same formula. I'm going to work this out in two different ways, actually. So I'm going to work it out the long way first. So if you don't like this, just hang on a minute. Negative log base 10 of, I don't know. I want to get my whole logarithm x term on its own. So I times both sides by -1. So I get -3.5 is just the log base 10 of x. And again, to get rid of the logarithms, you use the 10 as a base. You keep your answer as the exponent. So I would just type in 10 to the power of 3.5, negative 3.5. And I get x is 3.16 times 10 to the negative 1, 2, 3, 4. That's concentration, so it'll be moles per liter. Now, okay, different color. Let's show you the easier way. If you go back a couple slides, remember I gave you this formula here? Why don't we use that instead? Oh, that's not where I want it. Whoops. So that formula is 10 to the negative pH equals concentration of hydronium ion. So I know 10 is going to stay as 10. Do I know the pH? pH is 3.5. Do I know hydronium ion? No. And so this shortcut puts me right to that step there, basically, and I'll get the same answer. So if you want to work it out longhand, go for it. You want to use the formula that's already been derived, take a little shortcut, go for it. Both work. Less memorizing if you use this one, because you only have to remember the one formula, but probably easier math if you memorize this one. Again, don't care. Both work. You pick yours. Now, we don't only need to use pH. There is also a thing called POH, which uses the same methods. So your POH, instead of using hydronium, you just use hydroxide. Now, you never hear people talk about the POH, right? Like everyone talks about like, oh, what's the pH of this acid, the pH of this base. But POH can actually make your math a little bit easier, and this is why. If you apply both the POH and the pH formulas to our ion product constant of water, remember that the ion product constant, which is 1 times 10 to the negative 14, is equal to your hydronium times your hydroxide, right? So I want to find a way to get pH and POH in here. And I know the way that happens is somehow I need to get negative logarithms involved. So I multiply both sides, I take the negative log of both sides. If I do it on both sides at the same time, I haven't changed the equation, right? So that's legal. It's like adding 10 to both sides or multiplying by 5 on both sides. I can negative log both sides. So this does the distributive property thing. So I now have the negative log of hydronium plus the negative log of hydroxide. And wait a second, negative log of hydronium is the definition of pH. Negative log of hydroxide is POH. And this is just a number. If I take in my calculator, what is the negative log of 1 times 10 to the negative 14? I get 14. Just literally the number. The answer is 14. And so I get this nice easy formula. 14 is pH plus POH. So if I say, hey, the pH of this is 10, that means the POH has to be 4. They always have to add to 14. The pH is 7, the POH is 7. They're the same. They always have to add to 14. And so this makes things real easy for us. So for example, I know the pH of a solution, because you're always given pH. It's the common number. The pH is 9.2. 9.2, bigger than 7. This is a base. What am I worried about? The concentration of hydroxide. Now, if I use the pH formula, it's going to calculate the concentration of hydronium, which I could then plug back into the ion product constant, and it's just a lot more math. why don't I start with POH instead? Whoop, 14 equals pH plus POH. So if I know my pH is 9.2, I can just subtract 9.2 from both sides. And I know my POH, 14 minus 9.2. Probably could do that in my head, but I want to make sure I don't get it wrong because I don't want to have to re-record the whole thing. So my POH is 4.8. And now I can use the exact same formulas I used before. 10 to the negative POH instead of pH gives me hydroxide concentration. So if I use hydronium here, I get hydronium there. If I use POH here, I get OH there. Same formulas apply just as easily, and this will give my answer directly. 10 to the negative 4.8 equals whatever my hydronium is. 10 to the power 4.8 negative. So it turns out my hydronium ion concentration is 1.58 times 10 to the negative 5. Now, one last thing I want to talk to you guys about is how to double check these really quick. So neutral, right? Water. Let's make a new slide. In pure water, concentration of hydronium is the same as concentration of hydroxide, and they're both 1 times 10 to the negative 7. So basically what you're looking for is if acidic, if your pH is less than 7, you know that your concentration of hydronium should be greater than neutral. And neutral is 1 times 10 to the negative 7. If you're basic, so that means if you're given a pH that's greater than 7, you know that once you've calculated your concentration of hydronium, it needs to be less than 1 times 10 to the negative 7. You got to be less than neutral. So if you're basic, you'll be less than neutral for your hydronium. You'll be more than neutral for your hydroxide. And you can, this rule will work for hydroxide as well. You can flip it. So let's look at this example. Solution, pH is 9.2. That means we are basic. So what am I expecting? I'm expecting my hydronium to be less than 10 to the negative 7. And I want my hydroxide to be more than 10 to the negative 7. What did I calculate? I calculated hydroxide. Is that greater than 10 to the negative 7? It is? Perfect. Then I probably did it right. So just a quick way to think about your answer and double check it is just look at basically this exponent. Is it bigger or less than 10 to the negative 7? And does that make sense for the pH you're in? So that's kind of a little tip and trick for how to deal with the pH scale, a few examples of what the pH scale, or how to manipulate the pH scale, and kind of where it came from. So thanks for watching, guys, and that pretty much sums up our pH lesson for today. I will catch you next time.